Okay, so here we are, 8.3, all about quotients. So in the last section, we went over how to multiply radicals. And remember the basic rule that we learned in the last section, that if you have like the root of 3 times the root of 5, you can multiply those things together to get the root of 15. Or you can go in the opposite direction, right? You could start with the root 15 and split it up into 3 and 5, if that helped you out. So let's go over dividing rational expressions here. Irrational expressions, it should say. So when it comes to irrational expressions, one kind of the most basic thing would be this first example, right? You can see here they gave us two roots, one over the other one. Both are simplifiable. So if that's the case, you just simplify them right off the bat, and then further simplify whatever you have left. So 10 over 2 equals 5. Sometimes that's not the easiest route, right? Sometimes it's going to help us out to do what they've done here in this rule. They've taken two separate square roots in a fraction and turned it into one big square root over the fraction. So you kind of extend the root over the fraction, if that's helpful. Some cases that's not going to be helpful. Most of the time, if you start out with two separate roots, you know, the right move is going to be this next step to extend the root over the whole thing, but not all the time. Okay, so here's an example. We don't have, there's no, 27 is not a perfect square, right? 3 is not a perfect square. So I'm going to extend this over both, or over both those numbers. So root 27 over root 3 becomes the root of 27 over 3. 27 over 3, that equals 9. And the root of 9 is 3.
Sorry. It's just been in my head for forever, and I've been wanting to say it.
That's awesome. That's awesome. I like that one. Okay. Right, and so, you know, if you start out and you can't really do much, try to extend that square root, see if you can simplify into something where you can do something with it. All right, so here's another example. I'm not sure what to do with this, but I know that I can simplify some things if it's all under one fraction and one root. So I extend the square root over the entire fraction, and I have 8a to the 7th over 2a. Now, 8 over 2, that simplifies into 4. And then a to the 7th over just a plain old a to the 1. I use the quotient rule on that, right? Yeah, so it should be a to the 7 minus 1, right? Which I already heard somebody say, a to the 6th. Exactly, exactly. All right, so I have root 4, and I'm going to split these up because I know I can simplify them, times root a to the 6th. Okay, now that I see I can simplify both of these things, right? Root 4, I say, what's the square root of 4? Well, that's just 2. Yep. And then remember, I'm going to do the intermediate step here. So remember, I can rewrite this into terms of squares. I can rewrite that as a cubed squared. Right? And since I can rewrite it like that, I'm allowed to pull out what this middle thing is, a cubed. So this gives me 2a cubed. Right? If you can't remember all that stuff, just remember, if you have an even power inside a square root, to simplify that, you cut the power in half. That's it.
So you had a brownout.
What?
Instead of a blackout. Got it.
Cut it out. Yeah, okay. That's great. How are you now? All right.
Tyler's not here. Tyler, you're not here again.
Okay. So with this one, right, this is kind of like the opposite of the things we've just been doing. I can see right here that this is a perfect square, and so is this. So I don't want to simplify those at all to start out with. Not that I can simplify them, I don't think. But I can split the square root up into separates here, right? Because that's what makes it easier for me. So I have root 36 over root 25, and that gives me 6 over 5. Okay, here's another example like that. Once again, like I know 16 is a perfect square, so this is going to help me out to split this radical up. So I have root 1 over root 16. Don't overthink the square root of 1. It's just 1. Yeah, don't overthink that, right? 1 times 1 equals 1, so the square root of 1 is 1. Square root of 16 is 4. And that's it. We're done with that one. Here's another one along those same lines. Right? I split this up, root 49 over the square root of t squared. Root 49 is equal to 7. And remember, this is the definition of like a simplified square root. So we just pop out t. Any questions so far? Yeah, these are, I mean, this is not too bad. Not too bad stuff.
What was that last example? Like the last one was, no. It started with divide and then we jumped into, I keep track of my notes. Simplify.
Oh, okay. So yeah, you mean like we started with separate square roots and we extended the root over the whole thing, but there are other cases where you'll start with a large square root over the whole fraction and kind of have to do the opposite of that.
Sorry.
That's all good. It's a short lecture, so if you need any clarification, don't hesitate to ask.
I just like to know stuff. Okay, cool.
Okay. All right. So this one's a little bit weird. Let's see now. I'm almost tempted to split up the square roots in this one, but neither of these are perfect squares, are they? So I might actually simplify first, just to see what happens. So 14 over 50, if I divide both top and bottom by 2, I end up with 7 over 25. And that, to me, is a better result, because 25 is a perfect square, right? So I know what happens. And it's cool. Your phone just strobed at me. I was like, what's that flashing light? So, okay, so now that I recognize I have a perfect square on the bottom here, now it makes a little more sense to split things up. So I'm going to say root 7 on the top, root 25 on the bottom, and then that simplifies to root 7 over 5. Just something to keep in mind here, we haven't run into a problem like this yet, but if we have a radical in the denominator, that's not considered fully simplified. And so this one, because the radical's up top, this is considered fully simplified. But if we stopped with a radical on the bottom, we have to take a couple extra steps. So we're going to go over that in just a second. But remember, if a radical or a root is on the denominator, we don't consider that fully simplified. So let's do one more example like this, and then we'll find out how to rationalize denominators, which is what that's called. Okay. What's 48 divided by 3? I don't know what that is.
16.
What is it? 16. Ah. So I think we'd want to do that, right? Because 16 is a perfect square. So, okay. On our next line here, we end up with a 16 on top. And then pay attention to this. This is one of those examples where we have a larger number of exponents in the denominator. So remember how this works. I subtract 2 the denominator. And so I call this x to the 7 minus 3 down here. right? If I did that to the numerator, I'd end up with a negative exponent, and that doesn't do me a whole lot of good at this point. Right, so now I finally split up my radicals, and now I have some things that I can simplify. So I end up with root 16 up top, and x to the 7 minus 3, which is x to the 4th on the bottom. And I know how to simplify both of these. I get 4 over, remember, this is an even exponent, which means to pull it out of a square root, I cut it in half. The old Marcano brownout.
That's right. Not a blackout. Only brownout. Only going dark for a second.
That's awesome. Right, and then we'd be done, because there's no radical in the denominator, so this is fully simplified. All right. So now let's move on to rationalizing denominators. All right, so as we went over, an expression with a radical in a denominator is not considered fully simplified. When we do what we're about to do, we call this rationalizing the denominator, right? Because right now the denominator is irrational. We're about to make it rational. So to to rationalize any denominator at this level, all we do is we multiply top and bottom of the fraction by the rational portion of the denominator. In this problem, it's the whole denominator, right? So I just multiply top and bottom by root 2. Root 2 times 1 gives me root 2 on top, and root 2 times root 2 gives me 2. Be careful with this part. I myself am very tempted to write this equals 4 over here. Yeah, but that's not it, right? The square root of 2 is defined as the number. When you multiply by itself, you get 2. Yeah, that's a really common mistake. Okay, so this problem, let's just see how, just notice on this, the numerator is different, but the numerator really doesn't matter that much for this problem, right? So the radical part of the denominator was root 2. So I multiply top and bottom by root 2 here, and I get 3 roots 2 on the top over plain old 2 on the bottom. Okay. You might be tempted to think this is like a shortcut or like a workaround, but we're not allowed this either, right? If the square root is over the whole fraction, we want to get it out of the denominator. So we have to separate it first to root 5 over root a. Then I multiply, what should I multiply top and bottom by on this one? Root a, yeah. Right, root a. And that gives me the square root of 5a on the top over plain old a on the bottom. And also one common pitfall to avoid here is to try and simplify this even further from this point, right? Like if you've just rationalized the denominator, you might be really tempted to try and start canceling something out here. Don't do that. Just leave it. Yeah. Unless there's something like that's simplifiable outside of the radical, then just leave it. Okay. Let's try another one here. Actually, I might have to make a couple of these up as I go. So for this one, I can, there's two ways to do this. I might try it the long way, just because this is the proper way, I guess you might say. So on this one, I noticed that actually the denominator is simplifiable, right? So I could multiply top and bottom by root 45 here, but that's going to leave me more things to cancel out once this is all done. So I'm going to simplify the denominator before I multiply, or before I rationalize the denominator. So I have root 2 on top, and when I think about the number 45, I want to think about all its factors. Is one of those factors a perfect square? Obviously it is, otherwise I wouldn't have brought this up right now, right? 45 equals 9 times 5, right? And 9 is a perfect square. So we split 45 up into root 9 times root 5. Now on the next step, we simplify that root 9. So that gives us 3 roots 5. And so now, when I first started explaining how to rationalize the denominator, remember that I said we multiply top and bottom by the radical part of the denominator. So on this problem, that's only root 5. I don't need to worry about the 3 because it's not in the radical. So that gives me root 2 times root 5 on top. That's root 10. And on the bottom, I have 3 times root 5 squared, which is 5. And so in the end, this gives me root 10 over 15. Keep in mind on these ones, like especially in testing situations, if you have the, if you have a calculator you can punch this into, or if you're good with your like low-level calculator and you can figure out how to punch this in, you can compare these two results. If these two things equal a different number for some reason, something went wrong, right? These two things should be the exact same decimal. Okay. Here's another one where the example of the root all the way over the fraction. Right? Just remember that we want to split this up. Before I do that, though, I think I'm going to simplify these a's. Right? There's no reason not to simplify those, so that we maybe cut a little bit of work out for ourselves. So I end up with 7a over 12. Okay, because I canceled one from the top and the only one that existed on the bottom. That's how I did that. All right, so now I'm going to split up my roots. Root 7a over root 12. And I know I can simplify root 12 just a little bit. Root 7a 12 splits up into root 12 splits up into root 4 times root 3. And we know root 4 is a perfect square. So on my next step, I just simplify that, and I end up with 2 roots 3 on the bottom. Now, what should I multiply top and bottom by on this one to rationalize? It's root 3. All right. So when I multiply top and bottom by root 3, I end up with 7 times 3 on the top, which is root 21 times a. And on the bottom here, I end up with 2 times 3. Okay, so the root 3's just combined to give me a plain old 3. All right, and then the final step on this, root 21a over 6. Boom, we're done. Right, and so just to let you know, kind of this little simplification that I did right here, when I split things up and I simplified the denominator before I rationalized it, that ensured that I didn't have any more simplification when I came to this step. If you can't remember how to simplify your denominator or something like that, you're in a jam, you're in a test, and you just say, well, I'm going to multiply by the entire denominator. The only difference is you're going to have a little bit more simplification to do on this last step. I just like to do it first, but if you don't, then you just have a little bit more simplification on the last step. There's totally Jeopardy playing. Super weird. The first semester I did this class, one of our other math guys, Conan, was doing his class on the other side of the wall, and I don't know, he was probably annoyed with me too because I'm kind of a loud speaker, but he was too, and so constantly the wall's just like dun 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 because he's like writing on the board. You could hear him the whole time. Anyway, so that's how to rationalize the denominator. let's do a couple more problems just for fun here. And these ones are a little bit of review as well, as you can see. So on this first one, what do you guys think? Actually, take a couple minutes and try and see if you can find a perfect square that 350 contains, right? Let's do this one together, right? And so we are about to split this up into two radicals. One of these has to be a perfect square, right? The other one has to be whatever's left. So can you guys think of a perfect square that 350 contains? Yeah, it's at least 25. Good. 25 times what equals 350? 14, good. Thank you for that. I wouldn't have. Good, okay, and so let's see now. Does 14 contain any perfect squares? No. So that's it, we're good. Right? That was actually really easy. I thought that was going to be tougher, but Joey just simplified it for all of us. Right? Now, if you guys were thinking to yourselves, I don't know, I don't have any idea how to find that. Let me show you real quick. just so that, let me just show you over on this.
You look at me when you say these things.
I looked at it. I looked at the whole room. And like,
just look at Joey. It's okay.
All right. So if in the beginning I was like, dude, I don't know, 350, that's a big number, I would do a factor tree. And I'd say, I don't know, 10 times 35, sure. Then 10 splits up into 2 and 5. 35 splits up into 5 and 7. Yeah. And there it is. And I'd say, well, I have a pair of 5s. So I multiply those together to get 25. And then whatever I had left, the 2 and the 7, multiplied to give me the 14. Yeah, so that's it. That's how you would have found it if we didn't have Joey to give us a little boost. Right? But honestly, anything that's divisible by 25, like you can immediately say, well, I know 25's in there, so let me just see what else is left after that. All right, so we have 25 times root 14. We simplify the first part. Square root of 25 is just equal to 5. And root 14 just stays as it is. Okay? Everybody take just a couple minutes to try and work through number 2. Right? And remember, if we want to simplify something with an odd exponent, we split off one factor and then simplify the easy version. Take a couple minutes. All right. So you should have noticed, you should have just thought about splitting these two things up, right? We put our exponents under different radicals. So I have x squared, and then I have y to the 11th. X squared simplifies it to just plain old x. Sorry, the square root of x squared. The square root of y to the 11th, we can split that one up into y to the 10th times plain old y. We know, now that we've split things up, we have an even exponent, and so to simplify that one, we just cut it in half. So I end up with x, y to the 5th, root y. Okay. Now on this next example, I'm just going to multiply everything together first and then simplify that. So I'm going to put it all under one root. So I have 3 times 3, that gives me 9. x to the 4th times x cubed. That gives me x to the 7th. And then y and y, that gives me y squared. So once again, I just handle all these separately. So the 9 breaks off because that's easily simplifiable. The square root of x to the 7th, I'm going to change that into square root of x to the 6th times plain old square root x, right? Because I want an even power so that I can simplify whatever I can. And then I have square root of y squared. Now I just recognize that all of these things are simplifiable, so I'm going to write those out front. Square root of 9 is 3. Square root of x to the 6th is x to the 3rd. Square root of y squared is just y. And then I just have a root x hanging out there. Okay. Almost done here. Okay. I have things that I repeat like that over the semester, but they've changed like over the semesters. They used to make fun of me for something I used to say differently, like, yeah. What was I used to say? Right, flip it. Whenever it was a negative exponent, I used to say, oh, then we just flip this one. And people was making fun of me about that one for quite some time. Oh yeah, you just flip it? Like, yeah, just be quiet, student. All right, almost done here. So we got these two left over. So this one is just another classic example of splitting things up. Right, this gives us root 24 over square root of x to the 10th. Root 24 stays there, and square root of x to the 10th gives us x to the 5th. I'm not a stickler on this at this level, but you might want to just get in the habit of simplifying all your roots as much as you can. You know, like I said, I wouldn't take off any points unless I asked you to, well, now that I think about it, if I do ask you to simplify, you really should fully simplify. I won't be too much of a stickler about it though. But let's go ahead and fully simplify this one. So 24 splits up into 4 times 6. I know 4 is a perfect square, so I have root 4 times root 6 over x to the 5th. And then root 4 simplifies into 2. So I have 2 root 6 over x to the 5th. All right, and last one here. This one, right, neither of these are perfect squares, so it's much easier just to extend the root over the whole thing. 60 over 5. 60 over 5 is equal to 12. What does 12 simplify into? You'll start memorizing those after a while. So 12, remember 12 breaks up into 4 times 3. So I have root 4 times root 3, and root 4 simplifies. Any questions about these? Okay. If you're nervous about these, just go through and do a bunch of odd problems and look in the back of the book for the answers. I mean, these aren't long problems, so you could do 10 of these in like, you know, half an hour or less. So I'd recommend that. Yeah, and that's about it. We'll see you guys tomorrow. And remember, this is the last section of new stuff that will actually be tested on, right? And so we have closed out the testing stuff for now.
Okay. So
no, not for now, for the semester. Not for now. Right? And so what we learn tomorrow, you know, just come to class like, you don't necessarily need to take heavy notes. Just try and absorb the material and think about what it means. You know, it's kind of a weird thing that we're going to study tomorrow. It's functions. But yeah. And then if you've got any questions about these take-home packets, we can also go over those tomorrow. So if I were you, I'd look through these take-home packets at least and see if there's something in there that really just bothers you. And we can go over that problem tomorrow in class, okay? All right.